नहमदुहु व नुसल्ली अला रसूलिहिल करीम अम्मा बाद फ़अऊज़ु बिल्लाहि मिनश शैतानिर रजीम बिस्मिल्लाहिर रहमानिर रहीम रब्बी इश्रह ली सदरी व यस्सिर ली अमरी वहलुल उक़दतम मिन लिसानी यफ़क़हू क़ौली अल्लाहुम्मा अनफ़अनी बिमा अल्लमतनी व अल्लिमनी मा यनफ़अनी व ज़िदनी इल्मा वल्हम्दुलिल्लाहि अला कुल्लि हाल व अऊज़ु बिल्लाहि मिन अज़ाबिन नार। Bismillahirrahmanirrahim. This is Control Systems, and we are in Chapter 2 of Agoda's book, and we will study the modeling in state space system. And this is the generic state space representation of a system. We have a system matrix, an output matrix, an input matrix, and a feed-forward matrix that are defined for a system. And what state space modeling is, we define the state of the system at time t0 as the amount of information that must be provided at time t0, which together with the input signal ut for t0 state t is greater than t0 uniquely determines the output of the system for all t is greater than t0. So a state of the system is additional information to the input that is required to predict the output of the system, and there are state variables, and state variables hold the state of a system. And then a state vector is a vector that contains all the state variables, and a state space is a particular point in space that corresponds to the state of the system. And here it is important if we see what is the difference between classical control and state space control, and there are certain advantages. In classical control system, we solve the system or solve differential equation representing the system in the frequency domain. That is why we make use of Laplace transform, Fourier transform, and Z transform. However, in state space, we work in time domain in terms of matrices. In classical control system that is developed for a system that has only a single input and a single output, that is a CISO system, while the state space representation is not limited by number of inputs and outputs, and so it is more suitable for multiple input, multiple output systems or MIMO systems. In classical control system, all the mathematical operations are based upon the linearity property of the system, while in state space representation, the nonlinear systems can also be modeled. And in classical control system, however, there is an advantage. It's simple and intuitive. Once we are comfortable with the tools, then the system performance can be predicted very easily. It's intuitive. However, in state space, that kind of intuition is not available. We need to do complex linear algebra computations, but the good news is we use computers for it. Computers are very good for computations. In classical control system, we are pretty much blind to whatever is happening inside the system. Our main concern or what we are seeing at any given time is the input to the system and the output of the system. And in state space, we know the internal components as well. We know uh, the state of individual building blocks of the system, and maybe it's possible some of the internal components are going to saturation, but if we are observing only the output, we don't know what system caused an abnormality at the output. But in state spaces, we are keeping track of all the system variables that internal to the system, so we are getting a picture of every component. And in state space representation, uh, a system, although in classical control system we have a transfer function to represent a system, and that is pretty much unique. But in state space representation there is no unique representation. A system can have many unique, equally useful state space representations. And however, there are four major forms, and there are the major ones that have certain advantages, and we will only studying them. And the known as the canonical forms. The number one is controllable canonical form, with the observer canonical form. The two are combined, or they known as the companion form, and the controller and observer canonical forms are pretty much very similar to each other. Then we have the parallel canonical form, and unfortunately parallel canonical form is not possible in every case, and so in cases where parallel canonical form is not possible, we have another form, that is the Jordan canonical form, and it covers the limitations of parallel canonical form. And then we will start with the state space modeling. Let's start with the controller canonical form, and we are given a linear time invariant system defined by the following differential equation. We know it's a second order differential equation. Y is the output variable of the system, and u is the input variable. And any system, any LTI system, can be written as function of two variables, the input variable and the output variable. And this was the time domain representation, and we can take the Laplace transform. Yes, here we have taken the Laplace transform. So the caps represent a variable in the transform domain. So you see here, d square y by dt has been replaced by s square y, and whenever we are taking the transfer function, we are actually moving towards taking the transfer function of this system. And as far as the transfer function is concerned, it is calculated for zero initial conditions. We suppose that the initial condition y0 is 0, the first derivative of the output variable is 0, the second derivative is 0 as well, same as the case for input variable. Therefore, this is straight away converted to s square y, the first derivative replaced by an s, first derivative replaced by an s. So we have this particular equation. From here we can obtain the transfer function output over input. A few algebraic manipulations. Here is the transfer function, and for any of the canonical forms, before moving further, the step is we have the transfer function, and that transfer function should be in strictly proper fraction, that is, the degree of numerator should be strictly less than the degree of the denominator, as in this transfer function degree of denominator is 2, the highest power s is 2, and degree of numerator is 1, uh, the power of s is 1. Therefore it's a strictly proper fraction, and we can move from here. And same as you can for the other canonical forms. Okay, if for example the form is not the strictly proper one, or it's the proper form, numerator and denominator have the same degrees, and then the first step would be to perform long division and convert the fraction as sum of a constant plus a strictly proper fraction. And from here, for controllable canonical form, we have for each canonical form we have certain tricks. The one trick for controller canonical form is write this transfer function as multiplication of two fractions. One is the numerator fraction, the denominator fraction, and write y over u as multiplication of two transfer functions y over w dot w over u, where w is a new variable that we have introduced ourselves to make our life easier. How? Let's see. And then we suppose y over w is 2s plus 16, the numerator fraction, and it's important that when we are assigning the two fractions to variables y over w and w over u, what we want to do is write y and u as function of w, and all the s variables or s polynomials need to be multiplied on the side with w. So if I expand this, the term comes out to be this one. So y as a function of w in Laplace domain, and I can write it in time domain in this form. So y, the time variable, is 2 times the first derivative of w plus 16 times w. So this dot represents dw by dt, the first derivative of w. Same would be the case for the second fraction, right in here. And as you can see here, u is also written as function of w polynomial, and y is written as w polynomial as well. If this equation is written in time domain, we can write it as u is equal to 3 times w. W is the time variable, inverse Laplace transform of this capital W, then w dot, then w double dot. Next we define our state variable, and this is the previous slide we have seen already. And what we are now defining is our first state variable is x1, and we define x1 as w. Then we define our second variable x2, and we see x2 is the first derivative of x1, or its first derivative of w, right? It's how we move forward. Then we define our it's the second order. The system order was second. The highest degree of denominator polynomial was 2. Therefore, we need only two state variables x1 and x2. And in state space modeling, we need to write each of these state variables, its derivative as function of all the other state variables. And so now let's see, we have already calculated this equation in previous slide, y is equal to w dot plus 16w. So I will write y is equal to 2 times x2 plus 16x1. From where did come this x1? Oh, don't you remember? We already defined x1 is equal to w just a few steps back. Oh yeah. Then what's x2 here? In this, we define x2 as w dot. So we put it here. See? So y is 2x2 plus 16x1. We have this equation. This is the output equation of the state space modeling. And then from where does this come, this equation? Okay, you have seen it earlier. Where? Here. Remember? We have written this equation already. And as we have defined our state variables, w is x1, w dot is x2, and w double dot is x2 dot. We had to define only two state variables. The third is not required. So it's written, replace this form. One state variable with a derivative is allowed, second derivative is not allowed. So this equation is okay, and this can be rewritten as x2 dot is as a function of other state variables plus input. So this equation, and this equation, this complete our state space representation in controllable canonical form. You see, the equation 3 and equation 5 can be combined in a matrix form here. Right? I hope you know the matrix algebra. If somehow you forgot, see how we get the equation number 3. How to expand this matrix form. The first equation would be x1 dot is equal to 0 times x1 plus 1 times x2 plus 0 times u, and we obtain this one. The second equation x2 dot is minus 3 times x1 minus 4 times x2 plus u, this one, and then is output equation. So this completes our state space representation in controllable canonical form, right? And we can make a block diagram for this controllable canonical form. This is here, you see, and we have two state variable. That means in the block diagram we will have two integrators. So in drawing the canonical forms, we work with the integrator. We have some integration blocks, some gain blocks. So here is x1, and each of the integrator block has output is state variable, the input is the derivative of the state variable. So one of the state variables x1 is represented by an integrator. Then we have an other integrator for x2. And you see here x1 dot is equal to x2. Makes sense? We have the same signal. It's x2 here renamed as x1 dot. So it completes our first equation. See? Then we have to complete our second equation. In second equation we see x2 dot is minus 3 times x1. So x2 dot is minus 3 times x1, right? See here, x2 dot is minus 3 times x1, and x2 dot is also minus 4 times x2. This term also has to be added together. So we will have a gain block coming here, minus 4x2. See, we pretty much complete this again. How to complete this one u? Oh, we have an input that is coming here. Yeah. And now I completed our second equation. How to show this output equation? So that means we are having a contribution of x1 to the output. Multiplied by x1. x1 is weighted by 16 and x2 is weighted by 2. So x2 will come here. Here it is 2 times x2 plus 16 x1 is y. This completes controller canonical form. Da 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 da. Okay, and let's move to another canonical form, and that is observable canonical form. It's pretty much the same as the controllable canonical form. But the trick is different how to write it. Just pay attention. This is the same system we had seen previously in Laplace domain. Here, then there starts a trick. The trick is divide this equation by s square. Right? We have divided the whole equation by highest degree of s here, and the y it would remain here. All the other terms should go on the right side. Go on. And you see the different colors. I hope you see. And why different colors? Just observe the blue colors are the terms with s squared, and these greenish are with s. And if the degree would have been third degree equation, we would have s cube terms in a similar way, right? And this can be represented in this particular form. Confused? Shouldn't be. Let's see. This is the highest degree, h squared. So the trick is they combine the equation with the highest degree of s and write them here and write 1 over s outside. Right. Then go to the next degree of s, that is 1. Combine those terms, make a bigger bracket and multiply 1 over s and continue it. If the degree is more, keep doing it. And then we will define our state variables. Yes, it's important. We have to define the state variable. So the first thing is define this whole thing as one state variable. And I will define x2 first. Yes, y is equal to x2. Output is defined as one state variable. See here, this is x2, whole thing is x2. And if we ask what is x2 dot, this is derivative of x2 equal to, we can find it out. Okay, before you have to just work out for the question I just asked, what is x2 dot, we define the other variable x1, this other term, and similarly you have observed that when we define this term as x1, that meant x1 dot would be 16u minus 3x2. Why is defined as x2? So we say x2 dot would have been 2u minus 4x2 plus x1. This thing is x1, this is 2u, this is minus 4x2, and we're written this. Next is our representation is complete. This can be written in the form of a matrix here. This can be written as state vector form here. Y is only x2, but we have to write it in this particular form. A vector being multiplied with state vector. It's important. Yeah, next we have got to draw the observable canonical form, just the way we did it for the controllable canonical form. You see we have two integrators for x1 and x2, right? And if I observe here, x1 dot is minus 3x1 plus 16u, x1 dot is minus 3x2 plus 16u, right? Now how to write the second equation? x2 dot is x1 minus 4x2, x1 minus 4x2, right, plus 2u, this one, minus 4x2 plus 2u, is complete our observable canonical form. And we have the output as well, x2 is the output, so simple thing, make an arrow. Next is diagonal canonical form. Pay attention, it's probably the easiest of all, starting with the same system, Laplace domain, transfer function. The next step, the next trick actually is to what we did it. What's these are brackets? Okay, we actually did it. Factorize the denominator, right? We have to factorize it. And after factorization, we have to do partial fractions. Calculate A and B. 30. We can do it simply here. And this comes out, A comes out to be 7, B comes out to be minus 5. So this transfer function can be written in this form as well. And I hope you remember from previous slide, it should be in its strictly proper fraction form. If the two degrees are equal, then perform long division and then go for the other steps. Yeah, here if you can see here, this can be written in this form, right? Yes. Then so output is sum of two outputs. So this is system 1 y1, this is y2, y2 is minus 5 by s3u. That's why it's known as the parallel form or diagonal. It's also known as parallel form. We will have two parallel systems. Though both have been applied with some input u, the same input u, and their outputs is summed together to get the full output, actual output, right? That is it's also known as parallel form or diagonal canonical form. So y1 is this system, y2 is this system, and there is the same the previous slide we have seen it already. And then is so we have to define the state variables, rearrange them, and write it in time domain. Take obviously it's inverse Laplace domain. It's in time domain as x1 replaced by x1 dot the first derivative of x1, and it's can be written in this form in state space modeling. And then start with the second equation, the red one. Inverse Laplace transform. X2 dot is this thing, and this completes over. See, it completes our state space representation. Output is the summation of x1 and x2, and it's our state variable. X1 dot depends only x1, x2 dot depends upon only x2. This is a decoupled form. The two state variable are both are decoupled. And how to draw the block diagram? First, the top equation. X1 dot is minus 1 times x1 plus some u. Then the second state variable is minus x2 dot is minus 3x2 minus 5u. And this 7, by the way, can be written after here as well. This minus 5 can come here as well. And the output is this summation of two state variables. And then the Jordan canonical form, this is special form when uh, parallel or diagonal canonical form fails. We use Jordan canonical form. And where does it fail? When we have repeated which is pole, repeated factors of the denominator polynomial, here as plus 3 square. This system cannot be written in parallel form of 3 state variable. It's not possible. So the thing is, expand it, take partial fraction, and yes, partial fraction again, and we have this system now. See, s plus 3 is common, and we have an internal term. It's the same thing, except that 1 over s plus 1 is written as s inverse over 1 plus s inverse. This form is easier to draw the block diagram for this system. That means we will have a feedback system in which the forward gain is s inverse and the feedback gain is 1. And see here, this is our first system, right? S inverse over 1 plus S inverse times 7 by 2. This is our second system, minus 7 by 2, right? Here, this one, sorry, this one. And then we have another system, and these two are in series. We cannot make them the parallel. So these are going to be in series. This system is going to be in parallel to these two. And defining the state variables, we have three systems. X1 dot x2 dot is minus 3x2 plus x3, and actually we have defined it sort of a reverse. First draw the block diagram, and uh, I first do the block diagram you have seen in the previous slide. Sorry, I will reopen it. Unfortunately, the slides shut down. Just wait a minute. Sorry for the delay. Just wait. We were here. We were here. Okay. We first drew the block diagram. Then what we did was what we did is we assigned a state variable to output of each integrator and then wrote dot equations. That equations are coming forward. This equation and the previous system can be written in this form. I hope you can do it. And it's late in night. It's probably the time is now 11:15, and I am sort of going to sleep. And how to calculate D matrix? And earlier I said that if to convert the transfer function to state specification, or if the transfer function is not in strictly proper form, the first step is to make it proper. And the proper is make long division, right? Divide the numerator by denominator and write it in a simpler form. And what would be the question? Would be the D vector in state space equation, that is the output would have a summation of u. Like say the example here, we have this transfer function. The degree of numerator and denominator are same. Okay, it can only be same or lesser. Numerator degree would never be greater than the denominator for linear time invariant systems. And after long division, this can be written in this form. So 1 will remain here and the rest of the function is the one we will work with to convert to state space UK, right? And I will end my lecture here. Thank you, and may Almighty Allah protect you. Assalatu wassalamu alayka ya Rasulullah wa ala alika wa ashabika ya Habiballah. Labbaik, labbaik, labbaik ya Rasulullah. اللهم صل على سيدنا ومولانا محمد وعلى آله وصحبه وبارك وسلم.